two different displays and two groups of participants using one display. The first display is the one I presented before, our prototype using 3D laser register displays module. The other one is an optical see-through display, here the Movario BP30C. The display, whichever it is, was fixed on a frame. From this point of view, the observer could see a virtual or real target. The real target was this orange sphere mounted on a pole. And using a system of magnets and weights, we can precisely position this real target at the desired distance. Moreover, we recorded the position of the sphere using an OptiTrack tracking system. The virtual object was always displayed by the HMD after a short calibration phase using the red cross you can see here. Finally, the participant was asked to point the target with his fingertip. This finger was tracked using the OptiTrack system, and the participant was not able to see its hand during the answering. Our experimental design for this experiment was the following. So it was composed by three different conditions. The first condition was the distance of the sphere from 30 to 50 centimeters. The second condition was the type of sphere, which can be virtual or real. And finally, two groups of participants performed the experiment, one using the retinal projection display and the other group using OST HMD. Each participant performed 4 repetitions of the combination of these conditions, and 21 participants participated to the study. To analyze these results, we used a multilinear mixed regression model. This model shows a main effect of the object on the results, the type of the object, but showed no influence of the HMD. However, the interaction effect between the HMD and the type of the object was significant. As such, to better investigate the interaction effect, we perform a multiple linear regression analysis. So here are the regressions. We can see that this effect is confirmed by the regression. We can compare the two regressions for each device. In dark color, the regression for the real condition, and in lighter color, the regression for the virtual target. In fact, with the OST, the difference in estimates between real and virtual targets was from 3 to 6 centimeters. However, with the retinal projection displays, this bias was only from 0 to 2 centimeters. So retinal projection displays are closer to the real perception than optical see-through displays. We also evaluate the precision and consistency of the results, and in particular, we computed the quadratic means of the residuals. This shows that the estimates with virtual targets are less precise than the estimates with real targets. However, there is no difference between OST or RPD on the precision. This led us to think that the distance evaluation task is as difficult in RPD or OST. Moreover, we asked our participants to evaluate the difficulty of the task, and we didn't see any differences in the evaluation of the difficulty. As a conclusion, we can say that retinal projection displays provide a better distance perception than OST devices. These devices allow a perception of distances similar to the real perception, and they do not seem to impact the perceived or measured difficulty of the task. Those results are encouraging for the technology of retinal projection displays. However, more studies still need to be done to better investigate the effect of these devices on perception and their use in general for AR. Maybe retinal projection displays are the next generation of augmented reality displays, since they can provide the perception in line with the human real perception. This concludes my talk. Thank you for your attention, and I should be there to answer your questions. Thank you.
you, Ethan. That's a nice job. Now we will be having the few minutes like Q&A session. Either feel free to post your questions anytime during the Google chat or in the Q&A session in the individual paper set. Great. While we are waiting for the audience to type their question, one question for you. So know that the human visual system can sense multiple depth cues. Just curious about, have you guys considered incorporating a combination of multiple depth cues when comparing to their products?
I'm not sure I get the question right, but in fact, we focus here on as few depth cues as possible to really focus on the accommodation one, because the main difference between RPD and other displays is the accommodation. So we tried to get as less depth cues as possible to focus on this specific depth cue. But however, adding more depth cues can have an interesting effect, in particular in interaction between accommodations and other ones.
Good. I have a question from the audience. So how difficult is the display to align with users' execute?
The display is not so difficult to align. You have to have everything, since everything is fixed in our setup. The aperture is around 1 centimeter square, so it's not that small, and it's kind of easy to align it with the pupil. However, you must have something fixed, because for now it remains quite small, and 1 centimeter square is quite small, so have to be. It's easy to align, but you have to have a fixed frame.
Good. Seems like we don't have. So if you have further questions, feel free to post, and I think also will stay around and continue to. Okay, then let's send the speaker again and move to the next paper. Paper would be simulating the human visual system beyond real-world performance in future augmented reality displays. Here would be David from UNC. Welcome.
Hello, welcome to my talk on stimulating the human visual system beyond real-world performance in future augmented reality displays. We all know the promise of augmented reality. By making information and data more readily available, users can more easily make decisions and more quickly complete tasks. But does augmented reality have capabilities beyond making data acquisition more convenient? By definition, optical see-through augmented reality is capable of injecting additional visual signal, which both mimics the real-world image and manipulates it. There are many applications using this capability to affect the conscious perception of the user. But is it possible to also affect other human systems? What extent can we control and manipulate the visual signal beyond just showing virtual content? And what benefits can it have? Is augmented reality capable of augmenting humans beyond their normal ability? Can we improve human performance? These are some of the questions this work aims to answer. We set out to see what we could do with speeding up changes in gaze depth. So why depth changes? Well, under normal viewing conditions, gaze depth changes take a long time, sometimes upward of a second. That gives us a lot of room for improvement. Additionally, depth changes also consist of several human visual system responses working together. So there are a lot of levers to pull, so to speak. With the different speeds of each response, our task focuses on speeding up the slowest, possibly at the expense of the others, so long as the overall process is decreased duration. Interestingly, the previous literature shows that the responses speed up when working in concert with each other. So the graph on the left shows vergent speed and angle over time in the presence and absence of saccades. It is clear that the saccades speed up the vergence response. While the graph on the right shows the accommodation depth over time in binocular viewing conditions when vergence is operative and monocular viewing conditions when there are no vergence cues. Again, the vergence cues help speed up the accommodation response. The time to complete all three responses is reduced when they are all working together. But this happens normally during a depth change, so it is not enough to give us the speed boost that we're looking for. Additionally, all three responses have faster maximum velocities for larger movements. As seen in this graph of the velocity of accommodation over a 2-diopter motion and a 4-diopter motion, the maximum velocity is higher for the larger depth change. With those two insights, we decided to see if we could overdrive the focus change response. So much as a motor can be geared higher than the drive gear of a car, we wanted to test if such a mechanism could improve human performance as gaze changed depth. So normally, when looking from a distant object to a closer one, the gaze moves directly there. What we propose is for a brief period presenting an additional stimulus even closer than the target depth before backing it off to the target location. By thus overdriving the focus change response, we were curious if faster depth changes were possible. So we designed some user experiments. For our first experiment, we built a room-sized multiplane display with 4 depths, 33 centimeters, 50 centimeters, 100 centimeters, and 800 centimeters. Here are a few pictures of the physical display. As you can see, looking through the display, a virtual object displayed on any of the screens would be visible at that depth with the correct vergence and accommodation cues. Our experiment procedure started by displaying a fixation target on the far display, followed by a stimulus of randomly oriented Landau C-shapes. First at the overdriven depth for a time variable of t1, then at the target depth for the free variable duration t2, before changing to a series of O-shapes. The user was tasked with identifying the orientation of the C-shapes. We followed a staircase procedure to determine the perceptual threshold duration t2 for a given set of overdrive durations t1. We also tested a second condition where an 8-degree saccade was introduced to the same procedure. So with the 2 saccade magnitudes of 0 and 8 degrees tested over 4 different t1 overdrive durations, we determined the amount of time it took the user to recognize the orientation of the Landau C stimulus. You can see the results in the graph on the right, where recognition time is plotted for each of the 8 test cases. The black crosshatching on the bottom indicates the amount of overdrive duration T1 for each test case. Our goal is for the overdrive test cases to have a lower recognition time than the dark blue test case without any overdrive. As you can see, there's some indication of improvement for both saccade magnitudes, but it is much more pronounced in the 8-degree case. This demonstrates the increased velocity from the larger initial motion working in concert with all 3 motion responses to have a larger impact on the recognition time than when only 2 of the responses are present. So having all 3 responses together is important. While the test results showed a lot of promise, we needed to explore further in a larger study with more users. So we designed a second study. This study was designed so that more saccade magnitudes could be tested. We changed the back display to the LED targets at 2 different eccentricities. We also presented the Landau C-shapes on the display at 2 different eccentricities, which gives us a total of 4 possible saccade magnitudes at 7 degrees, 14 degrees, 21 degrees, and 28 degrees. We also simplified the study a bit by removing the largest overdrive duration, which hadn't shown any indication of improvements in our previous study. Here you can see some of the results from this larger experiment, showing the recognition time for each of the test cases of differing saccade magnitude and T1 overdrive duration, again indicated by the black cross hatching. A larger difference between the non-overdrive dark blue case and any of the overdriven test cases is our goal here. So the statistically significant results are indicated by the asterisks on the top of the graph, and you can see the details of our process for determining those in our paper. So here we can see two significant improvements, one in the 7-degree case and one in the 14-degree case. So in conclusion, depth changes take a long time. As AR practitioners and researchers, we need to be aware of that fact and design our user experiments with that in mind. However, in some test cases, overdriving focus response will decrease the recognition time required. There are several potential applications which may benefit from these findings. We are excited that they can be for both environments with augmented content, or if a user is wearing an AR device without augmented information being displayed, this process could still be used when depth changes occur. There's much work yet to be done. Devices with eye tracking and multifocal displaying have been demonstrated, but more commercially available displays will need to incorporate both of these technologies to take advantage of these findings. We also don't currently know when this method will work and when it won't. Further experimentation needs to be performed to determine the boundaries of when this technique is useful and when it is not. Many potential applications present themselves for this work, including possibilities for physical therapy, for delaying the onset of presbyopia, or other use cases. All be explored. And finally, we are excited by the potential this has demonstrated for AR devices to augment humans beyond their normal performance, and are looking forward to seeing other ways these devices can improve our capabilities. We would like to thank these people for assistance in developing this work. Thank our funding agencies, and thank you for your attention.
Okay, thank you, Debbie. So I think this is a very nice open question and engaging study. Although the work in this field is kind of still in its infancy, but I think it's really important to dive into this direction about the future AR display somewhat. So thank you for that. Okay, time for questions. Let's see. Again, feel free to post your questions anytime. While we are waiting for questions from the audience, I do have a question for you actually. So curious about how sensitive the response time would be subject to the brightness changes or color changes of the environment while you're doing the study. So I think the human visual system may show different response levels, varying the pupil size, for depth, for perspectives, and maybe to wavelengths. So have you considered including this in your study?
Right, yeah, the brightness and the environment that this is in would probably change the effect. I mean, as we look from far to near, our pupils actually dilate. It's part of the automatic response of our eye system. So that would probably take an effect. We unfortunately weren't able to test that in our location. That would be a great test for future work. Yeah.
Thank you. Yeah, we have a question on the Hoover chat. So the question is, placement of physical target, for example, a finger, closer than the actual target after viewing a distant target accomplish the same thing with switching the version/accommodation without augmented reality.
Sorry, I didn't follow.
Oh, okay. I can repeat the question again. You can also check the Hoover. So the question is, with temporary placement of a physical target, for example, you place either your finger closer than the actual target after viewing a distant target, accomplish the same thing with switching the version's accommodation without AR.
Let's see. Physical target. Possibly, yeah. I mean, in our experiment, we were just placing a virtual target there because, I mean, augmented reality displays allow that. In the real world, you could probably place a physical target at the closer distance as well, and that would, I mean, as long as you were able to move it quick enough, then it would probably work as well. Yes.
Okay, if no, then let's thank the speaker again. Thank you. Okay, just a reminder, you can also raise your hand and unmute yourself to speak over for questions here. Let's move to the next paper. Paper would be full face mask display with expression recognition, ready photoreflective sensor arrays. Here is Nari Takegawa from Japan. Welcome.
Hello, everyone. My name is Yoshinari Takegawa. I am an associate professor at Teaching University Hakodate. I'd like to present our research, digital full-face mask display with expression recognition using embedded photoreflective sensor arrays. The co-authors of this work are Yutaka Tokura, Akino Umezawa from Teaching University Hakodate, Katsushiro Suzuki, Katsutoshi Masai, Yuta Sugiura, Maki Sugimoto from Keio University, Genova Martinez, Placencia, Sridham Subramanian UCL, and Keiji Hirata from Fuji University Hakodate. To illustrate our work, I'd like to start by showing you the demonstration movie of the proposed digital mask. E2 Mask Z is a digital mask that can change the appearance of your face in any way you like. Unlike conventional avatar-based face-to-face communication in a virtual environment, E2 Mask Z can augment the wearer's facial expression with a favorite avatar in any real environment. Our integrated system embeds optical sensor arrays on the inside of the digital mask display to sample facial movements, and utilizes a machine learning technique to recognize the wearer's facial expressions. The face is the most expressive part of our body, and is one of the important parts that decides the impression a person makes on others. Psychologist Moravian states that the factors in deciding the first impression made by someone at a first meeting are made up of visual information, 55%, oral information, 38%, and verbal information, 7%. To create a desired persona that exceeds the physical limits of human senses, people have used digital avatars as more effective and flexible media to control the impression made on others in a VR environment. For example, in a remote video communication system, a speaker can digitally augment their real face by altering the appearance of a 3D avatar on a computer screen to look the way they want it to. Then, the speaker can flexibly manipulate the avatar's facial expression through a camera-based facial recognition system. On the other hand, researchers have also investigated several digital face augmentation technologies to customize facial expression in a real environment. For instance, Emotional Cyborg and Mouthover use a wearable display interface to augment the expression of the eyes and mouth with pre-recorded video image. Hyperface overlays the eye with digital animation through a half-mirror-based head-mounted display. Chromoskin augments conventional cosmetics with an electrically controllable thermochromic interface. To the best of our knowledge, these paradigital face augmentation technologies have lacked facial expression recognition capability. The users cannot control their augmented faces intuitively. To enable avatar-based face-to-face communication in a VR environment, researchers have investigated computer vision methods to estimate the facial expression of head-mounted display users. For example, headset removal and face VR model the facial expression covered by a head-mounted display using machine learning techniques, and reproduce the dynamic facial expression to an avatar. And thus not applicable to face-to-face communication in a real environment. To digitally augment the face in a real environment, we have previously explored a camera-based digital mask display, E2 Mask. As the critical design problem, 9 inches of camera-to-face distance is required to recognize a full facial expression, which makes the digital mask display too bulky to wear and walk around in real space. To address the wearability issues of face augmentation technology, we present E2 Mask Z, a digital full-face mask display with facial expression recognition capability. E2 Mask Z integrates a thin, flexible face mask display with photoreflective sensor arrays to enable facial expression recognition at a millimeter-short range. The integrated system identifies the wearer's facial expression based on the photoreflective sensor data and produces an avatar presenting the same facial expression. The 40 photoreflective sensors are laid out on the inside of the face mask display. We deploy an OLED-based flexible face mask display to keep the distance between the photoreflective sensor arrays consistently at a minimum distance from the face and smoothly overlay the convex human face. The workflow process of E2 Mask Z follows 3 steps. The face capture mask first samples the wearer's facial expression at 40 feature points around the eyebrows, cheeks, eyes, and mouth. Given sampled sensor array input, the system identifies the wearer's current facial expression, utilizing the trained support vector machine model. Finally, the face mask display renders the identified facial expression to the avatar face on a curved display screen. E2 Mask Z can identify 10 types of facial expression. We selected number 1 to number 5 based on the constant expressions defined by Ekman. Number 6 to number 10 are the facial expressions formed when pronouncing Japanese vowel sounds. We chose support vector machine SVM method to identify facial expression as it has the advantage of low computational cost and its feasibility for facial expression recognition using photoreflective sensors has been reported in prior work. We use RBS kernel and C equals 10, gamma equals 1.0 as hyperparameters. The avatar's facial expression parameters, vector P, such as the degree to which the left and right eyes are open and the width of the mouth, as shown in the figure on the right, can be composed by the formula shown here. This method refers to the work of Suzuki et al. We recruited 7 university students, 4 female, 3 male, for an experiment to confirm the facial expression identification accuracy. In the process of the experiment, each subject first put on the prototype mask, then was instructed to imitate facial expressions number 1 to number 10. For each facial expression, 10 data samples were collected. Since we repeated this experiment 6 times for 10 different facial expressions, we acquired 600 samples in total per subject. It took about 3 minutes to collect 600 samples of data. 6-fold cross-validation was applied to the sample data. As a result, the accuracy was 79%. We think this constitutes high accuracy, but we need to improve the accuracy of anger and surprise especially. Among the correct data for surprise, 63% were estimated to be surprised, while 12% were estimated to be ah. In contrast, among the estimation data for surprise, 15% were correct data for ah. From these results, it can be said that the surprise facial expression is being misidentified as the ah facial expression. The facial expression with the second lowest accuracy was anger. The high rate of misidentification in anger and sadness could be due to the fact adult subjects don't express anger or sadness daily, leading to the difficulty of producing clearly discernible expressions. To evaluate the feasibility of E2 Mask Z, we conducted user experiments to compare the sense of self-agency and self-ownership towards a controlled avatar between E2 Mask Z and a camera-based digital face mask display, E2 Mask. We recruited 4 female and 3 male university students. The task of the experiment was to reproduce 5 emotional states of facial expression. The subjects were instructed to practice facial expression control of the augmented avatar face for up to 20 minutes for both digital face mask displays. After the practice, we asked each subject to wear one of the digital face mask displays and guided them to a seat facing a wide mirror so that they could look at their entire body with the augmented avatar face reflected in the mirror. To make a counterbalance, we asked 4 of the 8 subjects to start the experiment with the E2 Mask Z and the other subject group to start with the E2 Mask. All the subjects were asked to memorize the top 5 emotional expressions, then reproduce the facial expressions in a randomly instructed order without the reference images during the experiment. After the end of the experiment, we asked the subject to answer 3 questions about the usability of the 2 digital face mask displays. Question 1. How well did the avatar recreate your intended facial expression? Question 2. How smoothly did the avatar's facial expression change? Question 3. How strongly did you feel a sense of self-ownership towards your augmented avatar face? Subjects answered on a scale from 1 to 5, giving reasons for their answers. Question 1 and question 2 evaluate the sense of self-agency, and question 3 evaluates the sense of self-ownership. This table presents the mean value, the standard deviation, and the significant probability of both E2 Mask Z and E2 Mask for each item in the questionnaire. Regarding the average value, a smaller value indicates a more positive response to the question. The 2-sided significant probability was calculated by performing the Wilcoxon signed rank test on the results of each question for E2 Mask Z and E2 Mask. Overall, subjects showed positive responses regarding the sense of self-agency for reproducing the expected augmented facial expressions with both digital face mask displays, and there was little difference between E2 Mask Z and E2 Mask. The proposed method can currently only recognize 10 facial expressions at the same time. To address this limitation in our future work, With more high-density micro-photoreflective sensor arrays, we plan to construct a 3D physical spatial model and track micro-expressions to enable smoother facial expression transformation in the augmented avatar face. The potential mismatch of the sizes of the digital face mask display and the face of the user is another practical problem to address. When the mask is much smaller than the user's face, some photoreflective sensors touch the face and fail to obtain the corresponding facial features correctly. As a simple solution, an extra nose pad or padding around the edge of the mask can be added to overcome a small range of mismatch between the facial feature points and sensor array positions. To overcome significant size differences, we must make new masks of different sizes to allow us to cover a user face size range that includes particularly small or large faces. As applications of E2 mask set, we can think of enhancement of facial expressions for patients with amyotrophic lateral sclerosis, ALS, a method to relieve fear of the dentist for child patient, and reduction of emotional labor for workers in customer service. Other application scenarios include changing online gamers' faces to look like their online personas during offline meetings, controlling the face of an interviewer to ease an interviewee's nerves, and augmenting the faces of performers for immersive stage performance. In conclusion, we created a digital full-face mask display with expression recognition using embedded photoreflective sensor arrays. We successfully demonstrated the proof of concept prototype, which integrated a flexible OLED display with a millimeter proximity sensing facial expression recognition system. It consisted of 40 photoreflective sensor arrays and a 10-class facial expression recognition model based on SVN. Our experimental results showed that proposed facial expression recognition system can classify the facial expressions with an average accuracy of 79%. The user study of the sensor's self-agency and self-ownership towards a controlled avatar facial expression suggested the photoreflective sensor-based facial expression recognition system has high feasibility in terms of recreating the expected facial expression. That concludes my presentation. Thank you for your attention.
Okay, thank you for speaker. Very interesting work. So now time for questions. Again, you can either choose to post your questions on Google Chat, or if you feel like you don't have enough time to type your questions on the chat, you can also raise your hand here and unmute yourself and speak here. So if you look into the bottom of the VR platform, the window, there's an item called raise hand. So you can raise the hand here and let us know, then speak out your question here. See if we have questions. And one interesting question, also something that I would like to ask too. So the question is, was the sensor array able to accommodate different users without recombination? Also, were the users limited in their motion at all by contacting the sensor array or housing? So basically, the question is about how robust or how generalized the sensor array would be subject to different users.
Hello, can you hear me?
Yes.
Hello, hello.
Yes, we can hear you. Hello?
Oh, okay. So it's your voice is choppy. Could you
Yeah, I can repeat the question. Question is about, was the sensor array able to accommodate different users? Also, were the users limited in their motion or by contacting the sensor array or housing? So it's about the robustness and the generalization of the sensor array subject to different users and different users' movement.
Oh, thank you for your question. So it's a first question about the our arrays. Hello, can you hear me?
Yes, we can hear you clearly. So the question is about, if you switch to another user, do you need to recalibrate sensor array? Hello?
Yes, I can hear you. And the other user their mask. The user have to calibrate again in this current algorithm.
Okay, I guess there's some unstable connection between the speaker and us. So I guess, yes, it might need to recalibrate the sensor array. But I would like the speaker to stay online and we can discuss about this question later offline on Uva. Yeah. Okay. So there's another question about like in terms of the recognition. So I would guess you are using the machine learning technique. So what kind of like database did you guys use for the training process?
Thank you for your question. So we make a data set about 10 facial expressions, for example, smile, angry, etc.
Okay, let's thank the speaker again. Thank you so much. And if you have any further questions, feel free to send a question to Hoover Chat, or you can directly contact the speaker, the author. So much.
Thank you very much.
Let's move to the next paper. So the fourth paper would be color more reduction and resolution improvement for 3D display using multiple wobbling optics. Speaker is Saoki Sasaki from NHK. Welcome.
I'm Seiki Sasaki from NHK Japan. Today, I'll talk about color more reduction and resolution improvement for integral 3D displays using multiple wobbling optics. Integral 3D display is an ideal 3D display based on integral photography method. This display can reconstruct true 3D image as like as real object. We aim to realize the same integral 3D display using a high-density direct-view flat panel. One of the issues is the occurrence of color more on a 3D image. As shown in this figure, integral 3D display arranges the display panel and lens array at the focal length of the elemental lens. So color more due to the RGB suffix structure occurs in the 3D image. Reducing resolution problem at deep position is also a big issue. I will talk about the technology for reducing color more and improving resolution by time division wobbling. I will explain about color more of integral 3D display. When the white letter A is displayed as 3D image, color more will occur if the subpixel structure is arranged with RGB pixels in the horizontal direction. The spatial frequency of this color more is generated as shown in this equation due to the relationship between the pixel pitch and the lens array pitch. In order to reduce this color more, conventional display devices have inserted a diffusion film between the lens array and the display panel. However, this reduced the resolution of the display panel, and the resolution of the deep 3D image is reduced as shown in this graph. Therefore, even if a higher density display panel was applied, it was not possible to obtain a 3D image that fully utilized its characteristics. We have previously prototyped a system that combines multiple flat panel integral 3D displays with a half mirror and have demonstrated the effect of reducing color more and improving resolution. However, the optical system was bulky. The next step, it is required to eliminate the optical system and realize the same function with an optical system. We will do that using wobbling technology. It is used as a technology to double the resolution of projectors by time division. We apply to it to a flat panel display. Traditional wobbling technology uses a birefringence element such as a quartz plate. The size of the quartz plate that can be cut out from the ingot is about several centimeters square. Therefore, it was difficult to increase the displayable area. And since the shift amount is small, there is a problem that thick quartz plate is required to secure the required shift amount. If the element becomes thicker, the constraint of installation within the focal length of the lens array cannot be met. Therefore, we thought about making it wider and thinner by using a polarizing diffraction element. The principle of wobbling using a polarizing diffraction element is shown in the lower left figure. The linearly polarized incident light from an LCD is converted to circularly polarized light by a quarter wave plane. After that, it passes through the liquid crystal polarization controller that switches the polarization direction and enter the polarization diffraction element. Here, it is diffracted in either the positive or negative primary direction depend on the polarization direction of the light beam. And as a result, it is spatially laterally shifted and output. This time, using this optical element in 2 steps. The subpixels in the Bayer array are time divisionally shifted horizontally and vertically. This is the experimental setup. The elements explained on the previous page are layered on the 9.6-inch dual green 8K LCD panel. Since the total thickness of the elements is approximately 5 mm, it can be used for lens array with focal length longer than that. This time, we use the one with 8.85 mm. Since the frame rate of the display panel is 60 Hz, the frame rate is equivalent to 15 Hz, which is a quarter of the frame rate for 2-step wobbling. This is the experimental results for reducing color moire. The graph on the lower left shows the result of cutting out the white background and adding the averaging 12 lenses in the vertical direction for red channel. When the spatial frequency of color moire was extracted and its intensity was examined, the measured value with wobbling in this system become 25%. The theoretical value calculated from the difference in wavelengths is about 20%. This difference is considered to be due to the pixel aperture and brightness distribution shape. You can see that there is an improvement effect from the result plotted on the CIE XY chromaticity diagram at the bottom right. Next is the result of an experiment on improving the resolution at a deeper depth position. In the experiment shown here, all objects were shown to be placed 250 mm behind the lens array surface. You can clearly see that the red Stanford Dragon was improved reproducibility, especially for the dorsal fin and face. In the ridge chart, what was seen as the color moire was improved, and it is now possible to display even higher frequency parts. The Nyquist limit of is different for vertical and horizontal because we use a delta arrangement lens array. This is the display result of the background and 3D image created by computer graphics. With wobbling in the figure above, color moire is reduced and the resolution is improved. Compared with the one without wobbling in the figure below. An example of a full parallax 3D AR display using a half mirror and experimental results are shown. Displays down for Dragon were shown to be placed 250 mm behind the lens array surface. I actually put my hand in the space at the same depth. It is expected to be applied to interactive contents. Then it is the conclusion of this talk. Two-step wobbling using a polarization diffraction element is mounted on Integra 3D display. Color moire reduction and resolution improvement are confirmed. Conventional diffusion method of synthesis or synthesizing method has a problem, trade-off with the resolution or device size. Proposed time division multiplex wobbling method realized thin and high resolution integral 3D display. The following is our future work. Applied high frame rate display panel, larger size of optical element, complete moire suppression, and realizing of thin 3D air display. That's all. Thank you for your attention.
Okay, thank you, Sasaki. And yeah, very nice work. So time for questions. Free to pose your questions, or you can just raise hands and speak out here. So yeah, the images look nice. So I'm just wondering, have you guys conducted the human observation study on the display scene?
Hello, thank you. Now, in this experiment, we made experiments just a few persons.
I think, yeah, that could be the future direction that you can do for the I have in mind is like, those like experiments shown in your slides, you are using the Bayer array LCD panel. Just curious why you choose this kind of panel. Who have specific requirements on the Bayer pattern, or also on how the pixels need to be aligned?
Okay. We used in this experiment we used Bayer array panel because it is a most in this time. This panel has a most preciseness and high resolution display we can get. So now we are challenging to this to use ordinary vertical 3 RGB stripe pattern panels also.
Good. Yeah, I think that would be a more generalized like solution for like commercial LCD panels. Okay, good. Audience. Okay, then let's thank the speaker again. Thank you.
Thank you very much.
Okay, then let's move to our last paper in this new IP space section. Last one would be correcting the proximity effect in nanophotonic phase arrays. would be the TVCG special issue paper. And the speaker today is Sherton Sun from the University of Maryland, College Park. Let's welcome.
Correcting the proximity effect in nanophotonic phase arrays. Most of the VR and AR headsets available today rely on a stereoscopic vision for depth cues. They usually suffer from a limited number of focal planes, which leads to emergence accommodation conflicts. In this case, the brain thinks that you are focusing at one distance, but the muscles in the eyes think otherwise. The VAC is known to be a major cause of discomfort in VR and AR. Varifocal displays and live field displays offer a wider range of focal distances. However, they both have disadvantages, such as being bulky or being limited by optical diffraction. Holographic displays, on the other hand, recreate the optical waveform of a scene, naturally addressing the divergence accommodation conflicts. Additionally, holographic displays are based on optical diffraction. Smaller pixel pitch would only improve their quality. The holographic displays recreate a waveform by modulating the amplitude and/or phase of light waves. Phase modulation is more common. The liquid crystal on silicon spatial light modulators, or SLMs, have been the most widely used phase modulators for holographic displays. They modulate the phase by adjusting the refractive index of the liquid crystal with different levels of voltage. There are now SLMs with very high resolution and good refresh rate up to a few hundred Hz. Nanophotonic phase arrays, or NPAs, are phase arrays operating at optical wavelengths. Recent years have seen them being used for phase modulation in holographic displays, notably the 2013 Nature paper from Professor Wall's team from MIT. The biggest advantages of the NPAs in this area are their integrated light source and the super fast refresh rates. A laser can be directly coupled into the NPA and distributed to antennas to be emitted into free space via optical circuit. Also, our simulation shows that the similarly modulated NPA can complete a phase modulation cycle in 10 microseconds, suggesting a refresh rate of up to 100 kHz. The phase modulation in our NPA is based upon thermal optics. Temperature adjusts the refractive index and therefore the phase. The phase at the pixel is linear to its temperature above the ambient. It is therefore important to note that the temperature must be non-negative in the hologram calculation because there is no cooling capability. This thermal modulation leads to the thermal proximity effect, which put simply is the phenomenon where heating one pixel affects the temperature of nearby pixels. We model the thermal proximity effect as a Gaussian convolution. The severity of the proximity effect is represented by sigma. Larger sigma indicates more severe proximity effects. Our MPA design has sigma equal to 0.66 pixel. Other MPA designs may have different sigma values. The thermal proximity effect negatively impacts the phase modulation accuracy, degrading the quality of the foam imagery. It is therefore necessary to perform proximity effect correction, or PEC. We propose two PEC methods. The first is the iterative proximity effect correction, or IPEC. It is based on the well-known Gershberg-Sexton algorithm. We consider the Fourier hologram, where the object plane is far enough from the hologram plane so that the propagation can be approximated with a Fourier transform. This does limit our method to holograms of 2D images, but we believe that this is a reasonable simplification for the first step on this topic. Our IPEC method replaces the source amplitude constraint in the GS algorithm with the equations highlighted in yellow. The phase of waveform B is formed by applying the proximity effect to the corrected phase of waveform A. The function P sub k inverse is the inverse process of the proximity effect, considering the non-negativity. To be precise, P sub k and P sub k inverse should apply to the temperature. But since the relationship between the temperature and the phase is linear, we directly use the phase for simplicity. Since the proximity effect is a convolution, we can write the correction as a deconvolution to find if the method becomes very similar to the method in Gamaliel et al. 2016, we refer to this method as the basic IPEC method and use it as the baseline to compare our methods to. The second method is the proximal PEC or PPEC method. In this method, we use the proximal algorithm to find the non-negative phase x that minimizes the residual g of x, which is the difference between the formed waveform intensity u of x under the proximity effect and the desired image I. To enforce the non-negative constraint, we add an indicator function c of x to the cost function to be minimized. C of x is 0 when all entries in x are non-negative and infinite otherwise. The proximal algorithm involves iteratively evaluating the proximal operator. We use the accelerated proximal algorithm, whose pseudocode is shown to the right. The most technical part is probably the derivation of the gradient of the function g. I'm going to omit the details here for time's sake, but it is available in the paper and the supplemental material. We carry out computational simulations to validate the effectiveness of the proposed methods. We implement our methods in MATLAB and run the simulations on an Intel 9900K CPU. We tested our methods on these datasets. In the PPEC methods, we terminate the iterations when the residual change is smaller than 0.1% for 10 consecutive iterations. From the qualitative results, the IPEC method performs much better than the basic IPEC method and is able to produce reasonable results. However, it is still not able to effectively correct the high levels of proximity effect. The PPEC method has the best correction effectiveness of all methods compared, and is the only method that can recover text-rich images when the proximity effect level is high. We also show the average image quality measured with SSIM degrades with the increasing amounts of proximity effect for the basic IPEC and the IPEC methods. The PPEC method retains the best image quality at all proximity effect levels tested. The PPEC method is also much faster than the IPEC method. The processing time generally increases with the proximity effect level. A few discussions. First, smaller pixel pitch, which is usually good for holographic displays, likely leads to higher proximity effect levels as the pixels are packed closer to each other. This makes the proximity effect correction more important, and the PPEC method is currently the only method that can effectively correct high levels of proximity effect. Second, there are several proximal algorithms to choose from. We end up using the accelerated proximal algorithm because this way we only need to evaluate the proximal operator of the indicator function c, which is easy. Another proximal algorithm, the ADMM algorithm, theoretically has faster convergence, but it will involve evaluating the proximal operators of both c and g. The function g is nonlinear, and evaluating its proximal operator is hard. In practice, we find the accelerated proximal algorithm to perform faster than the ADMM algorithm. There are some limitations to the MPA and to our PEC method. First, the MPA itself emits light, so it is hard for it to be used in diminution like the SLM to modify the wavefront of incoming light. Second, the initial phase plays a role in our PPEC method. In rare situations, a bad initial phase may cause the PPEC method to get into a local optima. Third, even though the PPEC method is able to effectively correct the proximity effect at the sigma values tested, it could not handle extremely high proximity effect levels, such as when the sigma is equal to 1.5 or 2 pixels. Going forward, we would like to study how to accelerate the PEC methods. Right now, it takes the PPEC method on average 6.61 seconds to process one color image of 100K pixels on the CPU. We expect massive parallelization and other specialized hardware for Fourier transforms to significantly improve the speed. Also, digital holographic displays truly shine in displaying 3D objects. To calculate 3D holograms, our one naive method is to divide the 3D object into a stack of images and calculate the holograms for each image at their respective depths and display them one at a time with time division multiplexing. To do this, we will need to adapt our PEC method for Fresnel holograms. Alternatively, we could look into how to correct the proximity effect in a hologram that captures the entire 3D thing. Thank you.
Thank you, Shiltong. So great questions. So I think this is a very interesting direction. So we have witnessed like so many holographic display papers in recent years of SIGGRAPH, SIGGRAPH Azure, and even optics values. Popular research field, and in my own experience, the current bottleneck is mainly the limited image quality. Thus, it's great to see we have alternatives to regular liquid crystal on silicon-based specialized modulators. So it will be an interesting work. While we are waiting for the questions from the audience, I do have one more question. So if I understand it correctly, current results and analysis are mostly based on simulation. Am I correct?
Yes.
So what would be the challenging issues you can anticipate for enabling a real display prototype using this nanophotonic phase arrays?
So first, nanophotonic phase arrays have a different design has been, some different designs have been implemented. So we think it should be, it is definitely possible to manufacture these. The problem we are facing right now is because it is quite difficult to manufacture them. It may take some time. And another difficulty that I imagine, like I said, is right now in this method, we only looked at the Fourier holograms, which is good for displaying 2D images, but not so much for 3D objects. And correcting the proximity effect for 3D holograms, that'll be the next topic on this line of research.
I see there's a hand raised up from the audience. Feel free to unmute yourself and ask questions.
Okay, can you guys hear me? Hello?
Yes, I can hear you, Kang. Hello.
Okay. Hi, Zedong. Thank you for the nice presentation. I'm wondering if one wants to get a nanophotonic phased array today, what are the choices there? Like, is there any manufacturer that you can point the audience to?
I can. Well, the manufacturing is mostly handled by my collaborator. I can answer to some degree to the best of my knowledge. First, it is sort of the nanophotonic phase array is like designing a electronic chip, and at our university we had these machines called e-beam writer. So we give it a design, and it can print out a chip. And we are also looking at, because the accuracy of the e-beam writer that we have is not super accurate, it's not super high. We are also contacting other chip manufacturers to print our design for us. And because we don't have a huge quantity, there are some companies that handles like printing this small quantity electronic chips for academic purposes, but getting to work with them is well, we are still in the process of getting to work with them.
Thank you.
I do have another question, a minor one. So do you think there would be some crosstalk introduced by other degradation resources, like for the real holographic display? Because like if you want to prototype a near-eye holographic display, you will have other optics, other electronics, and then we introduce some other artifacts may or may not affect the proximal correction algorithm you guys have proposed.
Yes, definitely. I do expect there may be other artifacts. First, for example, the manufacturing artifacts, like because in our design, we expect a uniform amplitude on the array. But in fact, when manufacturing these chips, it may not be the case. And we actually, because our method is can be seen as a optimization method, we care about the final observed image, and we can model that artifacts into the wave propagation into the observed image, and solve that using the proximal algorithm. And there have been some recent advances using by putting a camera in the loop to calculate holograms, and that in theory can solve a lot of different kinds of artifacts. That is also something we may try.
Okay, thank you. So, any other questions from the audience? Okay, I guess that's it. If you have further questions, feel free to continue to post on Hoover. So I think the authors will like stay online for a while so they can like discuss, share more information to you. Okay, let's thank the speaker again. Thank you, Shelton. Okay, so concludes our new display section. Let's thank all the speakers again. Thank you. Please keep track of the Hoover platform to continue inspiring discussion and interaction with all the authors. I hope you all enjoyed the presentations today, and we have 5 nice papers. Also this nice virtual platform. I mean, it's an interesting exploration for me at least. So yeah, thank you so much for your attention. Enjoy the rest of ISMA. Cheers.
Thanks, Ivan. Hello, everyone. Back again. Thanks for this great session. Great papers. Congrats to all authors. Great to be here in ISMA. So we are going to have this half an hour cultural break.